Okay. Yeah, welcome everybody. My name is Felix Wolf. I'm the chair of the Department of Computer Science, and this year we are celebrating the 50th anniversary of our department. And as part of our celebrations, I'm very proud to welcome the recipient of the ACM Turing Award 2021, Professor Jack Dongarra. He received the award for pioneering contributions to numerical algorithms and software that have enabled decades of extraordinary advances in computing power and applications. And the Turing Award is called by some people the Nobel Prize of Computer Science. It's named after Alan Turing, the British mathematician who described the mathematical foundations and limits of computing. So Jack Dongarra holds an appointment at the University of Tennessee, in Knoxville, where he is director of the Innovative Computing Laboratory. And Jack, you also hold appointments at Oak Ridge National Laboratory and the University of Manchester. And Jack specializes in numerical algorithms in linear algebra, parallel computing, the use of advanced computer architectures, programming methodology, and tools for parallel computers. And Jack, you have received in your career countless awards and honors, and the list is so long that I cannot really name them all here. So, and I also feel that they're somehow implied by the Turing Award. And well, instead I would like to say something personal. So I had the honor of working for you for 2.5 years. And to me, you're not only an outstanding scientist, but also a role model as a leader, as a motivator. You're a source of inspiration. And your staff and alumni, they're like a big family. And I'm, even if I worked for you a very long time ago, I'm very proud to be still part of it. And yeah, before I hand over the floor to you, I would like to announce, so this talk is streamed and recorded. And now I look forward to your presentation.
Okay, well, thank you so much for that kind introduction, Felix. Felix was a postdoc with myself and my group at the University of Tennessee a number of years ago. When was that, Felix? What year was it?
It was from 2003 to 2005.
Okay, very good. And it was a pleasure to have Felix here. It's good to see he's gone on to bigger and better things, of course. So I'd like to talk about a few things, mainly about software. The work I'm going to talk about was funded in part by the National Science Foundation in the US and the Department of Energy. They're interested in high-performance computing. So we're going to look at a few things. We're going to look at how HPC, high-performance computing, has changed over time. We're going to look at the evolution of some software. We're going to look at what's happening today and maybe what some things are as we move forward in terms of high-performance computing. I'd like to start the story where I began my career. So I started work in high-performance computing back in the early 70s. And these are the two supercomputers that we had available to us. One was a CDC, Control Data Corporation, 7600, and the other was an IBM 370-195. So the 7600 had a 65,000 word of primary memory. So that's the memory in the machine itself that you had access to. The IBM system had a little bit more with 4 megabytes of primary memory. These machines were scalar computers. They were just a single CPU, but they had some really advanced features for their time in terms of the way in which they executed instructions. They had a highly pipelined execution stream, and they were actually capable of executing instructions out of order if it was to the advantage. So they had many features built into the hardware which gave them additional performance and made them really in a class of supercomputers for their time. And it was about this time that we became interested in development of mathematical software. There was a sort of a revolution going on in terms of numerical methods for solving linear algebra problems. And the linear algebra problems the algorithms were collected together in a handbook, and that handbook was edited by Jim Wilkinson and Christian Reinsch. And they put together the state-of-the-art for solving systems of linear equations, and those routines were expressed in terms of algol procedures. And it was at that time when I was working at Argonne National Laboratory on a project called the NATS project. The NATS project is a national activity for testing software. We had a project called LPack, and LPack was a software effort to take the algorithms in this handbook and construct Fortran programs from those programs. So we were taking, in particular, the eigenvalue components of the handbook and translating them into Fortran and then making them available. And the idea was to put into the software a number of what I'll call key features. And those key features are listed at the top here: accuracy, getting the community involved, having innovative state-of-the-art algorithms, looking at performance, portability, productivity, readability, and reliability. So we were really striving for portable programs. We wanted to have these Fortran programs go from one machine to another. Today we take that for granted. Today we have IEEE arithmetic, which makes that port quite easy. In the early days, there wasn't IEEE arithmetic. It was what I think of as the Wild West, where each computer manufacturer had its own way of specifying the precision at which the computations were going to be done, and that has a direct impact in terms of how you stop an algorithm or converge an algorithm in terms of the numerical accuracy. So we had to think through all of those problems and come up with a portable scheme for expressing things and making things available. If you know something about algol, the original code was algol and we translated it into Fortran. Algol stores things by rows. That is, the two-dimensional arrays are stored by rows, and in Fortran, those two-dimensional arrays are stored by columns. We did a very faithful translation of the algol into Fortran, which means we copied the algol row accesses, which was, in effect, a disaster for performance in the Fortran code, because that really disrupted the flow of data. It really hampered the pipelining of information that might occur. So those were sort of lessons that we learned. In the 70s, there was sort of a revolution that took place in terms of the architecture. We had not just scalar computers, but vector computers were emerging. And these are two classic vector computers for their time. The first one is a machine designed by Seymour Cray. He's standing next to his rather elegant piece of hardware, the Cray 1. This machine had 1 mega word of memory associated with it. It had a cycle time of 12.5 nanoseconds, and it had a theoretical peak performance of 120 megaflops, million floating point operations per second. When I talk about floating point operations, I'm going to talk about adds and multiplies. So that's the rate at which it can perform floating point addition and multiplication, 64-bit operands, usually when I'm talking about that. So about 100 of those Cray 1s were sold. There was another vector computer from Control Data Corporation called the Star 100. And that architecture used vector instructions as well. So a vector instruction is you issue one instruction and it has an effect across a large array of data, a vector of data. On the Cray instruction set, they had vectors to contain those things that were going to be operated on. So you basically stored or loaded information into those vector registers and then did the operation out of the vector registers. That was important because it allowed one to get reuse of data. So if you could reuse data that was already in the registers, you can get much higher performance because you didn't have to load it from memory into the registers. Data movement is extremely expensive. It's always been expensive, and that's really what you pay for in terms of the computing time that you're using. The Star 100 had a slightly different architecture. There were no vector registers. It streamed data from memory through the vector functional units and then back out to memory. So there was no chance of getting reuse of data. And the result of that ultimately was the Star 100 was not as efficient in terms of how it could be used for doing programming, where the Cray 1 was much more efficient. And by efficiency here, we're really referring to how close we can get to the theoretical peak performance of the machine. In the case of the Cray machine, it's 120 megaflops. In the case of the Star 100, it's 100 megaflops. It was easier to get to that 120 number than the 100 number on the CDC Star. And the vector machines prompted us to think about rewriting software. It prompted us to develop software packages that used vectors as the underlying structure. In linear algebra, that's not a hard stretch. We had a package at that time called the Level 1 BLAs. The BLAs are basic linear algebra operations. And the operations that we're talking about are vector operations. So things like dot products, things like taking a scalar multiple of a vector and adding it to another vector, doing a norm computation or a copy computation. Those are the vector operations that were defined by this de facto standard called the Level 1 BLAs. The community got together and defined a set of routines, the syntax and the semantics, that were ultimately coded up as a set of routines that were used. And they were used by a project I was involved in called LPack. So LPack is a package of mathematical software for dealing with systems of linear equations. IcePack was for eigenvalue problems. LPack is for systems of linear equations. And it was built on top of that package called the Level 1 BLAs to get performance on vector machines. We had vector operations. We thought we would get good performance out of it by using those as the basis, the underlying structure for designing the software. And we built a package called LPack. So LPack was designed by 4 people: Cleve Moeller, Jim Bunch, Pete Stewart, and myself. We were the architects, the software writers for that package. LPack today is often thought about as a benchmark, and I'll talk more about the benchmark. It had its origins in that package. In the 90s, the architectures changed again, and the architectures evolved from vector machines for supercomputers to machines that had a cache-based system. So information was brought from memory into a cache, and then it was hopefully you can get reuse of that data once it was stored in cache. Once it's in cache, it had very quick access to the functional units to do the actual operations. And the other thing that was happening is we were thinking about parallel processing. There were a number of companies that were making shared memory machines. Each processor could get access to a global address space of memory. So they all had equal access to it. They made memory references to that data, and data would come to the processors themselves. So all the processors had equal access to the memory. So that's the shared memory context. And there was a number of machines, number of companies that went into business to make this architecture, hopefully trying to sell it and become profitable from it. So a number of companies that are listed there, all engaged in parallel computing. It was an exciting time to be involved in computing. We had all of these test beds that we can try out our ideas on. All of those companies failed. That is, they couldn't sustain themselves. They couldn't sell enough machines to make them profitable, and they all went out of business. It was about that time that we decided to change our software and target it for those cache-based shared memory machines. So Jim Demmel at Berkeley and myself got together, and we decided to redesign IcePack and LPack and put it into a package called LAPack. So LAPack takes both eigenvalues and systems of equations. It puts it together in a uniform form. It structures them to use a set of routines called the Level 2 and Level 3 BLAs. So we had realized that vector operations were not the right level of expression and granularity for the underlying algorithms, and we wanted to raise the level of granularity to be not just vector operations, but to be matrix vector and matrix matrix operations. We wanted to express the algorithms in terms of matrix operations so that they can effectively use the cache that was on these machines. Matrix operations, you can think of them as matrix multiply is the simplest case. A matrix multiply takes 2 matrices. For simplicity, let me call those matrices of size n. So we have 2 matrices that we're going to multiply together mathematically. That process takes n squared pieces of data, order n squared pieces of data, and gives you back order n cubed operations. So matrix multiply cost n cubed operations. So you're going to move n squared, you're going to do n cubed operations once it's moved. On a cache-based machine, that's perfect for getting efficiency. So we structured the algorithms in LPack to use those blocked-based methods using matrix multiply as the central component of the implementation to express the algorithms to get high performance on those machines. And we had a package then which effectively did that. It was a Fortran package that was implemented and became in wide use in the community. It was about that time when new architectures were emerging. The new architectures that were emerging were parallel processors that had distributed memory. So the first incarnation was for shared memory. So we had a set of processors that had equal access to an address space, a uniform address space. In this context, we have a set of processors, each having their own address space of memory, and they have to be programmed to effectively use their own memory, but also share information, and that sharing is done by passing a message from one process to another. So in the programming that's done, one expresses message passing as the underlying mechanism for moving information between the processes. So we have parallel processing, we have message passing being required to do that, we have distributed memory associated with it, and we have a new set of companies that emerge which designed architectures around those concepts. And those companies are listed here. There was a wide collection of them, producing machines, that was intended for the scientific community. Those machines were developed, some were used, but all of those companies ultimately failed. So they went out of business. They went out of business because, in effect, there was not enough support to sustain that kind of business for those companies, and they went out of business. It was about this time that the idea of passing messages was important, and it was sort of a research topic, and a number of groups around the world were starting to think about having a standard for doing message passing. In fact, a number of groups developed their own mechanisms for doing message passing in the programming layers. So think about Fortran or C programs having a standard for passing messages between them on these parallel machines. And I've listed here a few of the names of the message passing systems. P4 was a system that was designed out of Argonne National Lab. My group in Tennessee designed a system called PVM, Parallel Virtual Machine. It was an interface for doing message passing that allowed machines to be used in parallel by communication. Intel, the guys at Caltech had something, and so on. So there were a number of different ways of doing it. And it was starting to be a little bit chaotic in terms of developing programs. I had to develop programs, ideally, I would like to develop programs that would be portable so I can take them from one machine to another, but in this context, I have too many message passing interfaces that I have to deal with. So we got the community together to say we need to specify a uniform way of doing business. So that group was called the Message Passing Interface Forum, MPI Forum. It got together, it met 3 days every 6 weeks, physically got together at a hotel in Dallas. We did that for about a year and a half, and at the end of that year and a half, we decided we had a standard. We had a form of doing message passing that we could live with and that should be available to the community for the community to use. We also solicited input from the community. But basically a group of 40 people got together with that frequency, and after a year and a half, we had the draft specification for MPI, and it quickly became the de facto standard. Manufacturers implemented it, and it was used from that point forward. MPI has a long history. It's evolved in many ways, but that was the origin of message passing. In terms of the software, we now had a mechanism for expressing programs in a very portable fashion. So we designed a linear algebra library around those Gauss routines, and also around the message passing library, to have a library that would work on distributed memory architectures. And that package is called Scala Pack. It was designed specifically for distributed memory. It had the ability to do matrix operations. It had built in all of the strengths of doing cache-based operations to effectively exploit that architecture. It was about the next 10-year period, the architectures changed again, and this time they changed to provide us with multi-core. So having many cores on a single chip, allowing for high performance operations to be carried out, usually with a shared memory paradigm for those processors, for those multi-cores on the chip. You know, we have Moore's law taking place here. We've got a lot of transistors that are capable of being put on a chip. Those transistors are being used in this context here to provide additional processors. So that chip has multiple processors now on that substrate that are capable of doing independent operations using a shared base of memory. We also had GPUs starting to emerge, which were capable of doing large-scale or 64-bit floating point operations. So the GPUs had their origins, of course, in graphics processing cards that helped with doing the graphics on a processor, but they soon had the ability to do floating point computations at the right level of accuracy that they could be very useful in terms of the scientific computing. And they started to be used as an accelerator, an offload engine, if you will, to allow parts of the computation to be shoveled off to the GPU where they can be done very efficiently, and then the answers coming back to those to the processor, the central processor, in this case a multiprocessor architecture. And that led us to redesign the software again. So we designed a package called Plasma that would be specific for multi-core, that would do its best job of optimizing the use of the multi-core in a shared memory context. That's what Plasma is about. We also had a package called Magma, which was capable of exploiting that GPU and getting as much performance out of the GPU, doing that offload so a lot of the matrix computations can run very efficiently in that context. The next architectural feature that appeared is the use of highly parallel systems. So I'm not talking about 10 or 16 or 128 processes. I'm talking about machines that have thousands of processes, tens of thousands of processes in them. And the common way we were exploiting parallel computing was to do a fork-join based kind of computation. So we fork off a number of tasks to be done in parallel on that small number of processors, and then we join together into a single thread of execution and perhaps continue on, maybe doing another fork. That fork join, that bulk synchronous processing, is fine when you have a small number of processes, but when you now have tens of thousands of processes, that join component is something which will interfere with the efficiency of the underlying algorithm and provide something which is very ineffective. So we had to come up with another mechanism for doing that parallelism, and a lot of ideas are in the air in terms of doing it. A lot of software was being experimented with. Our colleagues in Spain had a system that they were developing in Barcelona. The OpenMP community had designed some features in OpenMP that allowed one to express parallelism in the form of a directed acyclic graph. My group in Tennessee has a system called parsec, which allows that same kind of data flow computation to occur, and the guys at Stanford have a system called the Legion, and there are many more, of course. These are old ideas, these are not new ideas, but the time was right to take those ideas and to use them on the hardware that we have. So the algorithms that we were looking at went from a fork join kind of loop level parallelism into a form of parallelism that expressed the computation in terms of a directed acyclic graph, and then had a mechanism, a runtime system that allowed that DAG to be executed very efficiently. If you take a look at the directed acyclic graph and you look at the critical path of that DAG, the critical path is the one which will free up the most amount of parallelism, so the hope is that you can execute that critical path first or as fast as possible so that it'll free up as much parallelism as we had. And the other mechanism that we started to think about was using a batch-based system, and this was motivated by looking at machine learning. In machine learning, we have very simple operations on small matrices we have the same operation that's being performed over and over again on independent sets of data. So think of doing a matrix multiply, think of doing tens of thousands of matrix multiplies of small, dense matrices. We want to be able to express that in a way that could allow for the expression of that very simply and allow the underlying execution to occur very efficiently. And we do that through a batching operation. So you make one call that says we're going to do this operation on these independent sets of data, and then we let the underlying system schedule that on the hardware, whatever that hardware is, maybe a GPU, maybe a multiprocessor system, to effectively drive that computation. And that same thing could be used for other matrix operations. We have many cases where we want to do a singular value decomposition of small matrices, many thousands of them, and we have a mechanism now for expressing that at the programming level that can get very effective performance on the underlying hardware. So that led us to developing this thing called parsec, which is the DAG-based runtime system that I mentioned, and also a set of routines that we call the batched BLAs. And these, again, the batched BLAs are based on a community input, what the community felt is necessary, getting together the vendors, high-performance computing users, and basically the community to define what's necessary in this context so that a de facto standard can, in fact, go on. So we have CPUs and GPUs being used, and of course, we're not going to be satisfied with just putting one of them together. We put together a number of processors, CPUs on a board, together with a number of GPUs to carry out a computation, and then build a whole system out of that. In fact, the machine that we have at Oak Ridge National Lab is built out of just that context. So the architecture of a node of that machine at Oak Ridge National Lab, a machine that has an execution rate of peak of 200 petaflops, is based on two IBM Power 9 processors. This is one node, two of those CPU chips tied together with 6 of these NVIDIA GPUs to carry out the computation. So that's one node of the system, and that gets replicated into thousands of nodes on this machine to put together a parallel system that can be used to drive many of the simulations that are performed at Oak Ridge National Lab. How big is the machine? It's about 2 tennis courts is what you should think of as the area of the machine. And in terms of power, this particular machine consumes about 10 megawatts of power. So that's the power under load, 10 megawatts. So what's a megawatt? So in Tennessee, if I use 1 megawatt at my home, and I use that for 1 year, I'm going to get a bill for $1 million. That's approximately what 1 megawatt year looks like in Tennessee. It may be a little bit higher here in Germany. But that's what it is. So $10 million just to turn on the machine is the way you should think of that. But this machine is an expensive machine, so that's a small part of the overall cost of the machine. But that goes into the maintenance, I'll call, of the machine over a long period of time. So that machine's been operating now for almost 4 years. So that machine is about to be replaced by a newer machine, and I'll mention that in a moment. So we have a package that's designed for this architecture. So we changed the underlying software again. We designed a new package. This package is called Slate. It's intended to run on a machine which has heterogeneous nodes, CPUs, multicore, plus graphics processing units, accelerators put together in a form that can be done on a massively parallel scale, doing message passing, effectively coordinating the tasks, using an underlying system to do DAG-based, to have a runtime system that can execute that directed acyclic graph approach to the underlying structure, and hopefully be very efficient. Everything's being done in C++ based on those structures, and we have examples of that running on large-scale parallel machines. How large? 10,000 nodes is the kind of thing that we're thinking about, and on the order of 10 million cores if you identify things in terms of cores. So that's the structure that we have today. And we'd like to say our software runs on this pyramid of the computational structure that we use for doing scientific computing. We want our software to be run, of course, on the national centers, the big the big machines that have the fastest and most powerful computing platform, but also on laptops. So our Scala Pack software can in fact be run on my laptop. It requires no change to the underlying software. There's some libraries that have to be modified, but those are very standard libraries that could be attached to that process. Things like the BLAS and things like MPI that might be necessary to do that. So we'd like them to be run on that whole pyramid and effectively run so that they're efficient across that without having to make major changes to the underlying application. So from an application standpoint, we want to have an application developer implement something on a device and then take it to the next stage and not have to make major changes to the underlying software as they move up that pyramid, finally running on the high-performance computer. And we'd like to do that using these attributes: accuracy, getting the community involved, having state-of-the-art algorithms, performance, portability, productivity, readability, and reliability built into the underlying software. So the structure that we have today for high-performance computing looks something like this. It's a machine which has distributed memory. It's built on top of MPI and OpenMP as the programming models. There's a machine coming up today. Literally, as we speak, it is starting to be put into production runs, at least getting it up to speed, and that's a machine called Frontier. So Frontier is a machine that's at Oak Ridge National Laboratory. It's a machine that's funded by the Department of Energy. It has 8 times 10 to the 6 million cores in it. So 8 million cores in this machine. It has 9,000 nodes of the machine, and nodes are composed of 2 AMD processors, Multicore, plus 4 AMD GPUs. That makes up a node. They're put together using a high-speed interconnect that Cray manufactures, and hopefully providing basically a potential for 2 exaflops, 2 times 10 to the 18 floating point operations per second. So that's a machine that's just coming into play today. If you take a look at that machine, 98% of the performance is coming from the GPUs. So if you're going to use that machine and you're expecting performance, you had better be using the GPUs. So that requires you to rethink and re-implement your algorithms in order to effectively do that. Our libraries are intended to do that, and hopefully we can extract that performance. So heterogeneity is the way in which high-performance computing is structured today. Simple loop-level parallelism doesn't work on machines. You have to do something else to express more parallelism within your application. We want to be able to minimize the amount of communication. Communication is the thing which is the most costly thing on high-performance machines. It's not the floating point arithmetic. Floating point arithmetic has been over-provisioned on our machines. That basically is free. What you're paying for is moving data between one part of the machine and another part. So you want to minimize the amount of communication that you do. You could do that in a number of ways. One way would be to come up with algorithms that have provably the minimum communication associated with them. So we have a number of algorithms where we can prove that this algorithm has the minimum communication for doing this kind of a computation. Other ways are to try to get reuse of data whenever possible. Another way might be to exploit mixed precision. So think about exploiting 32-bit arithmetic if possible. So moving 32-bit operands around rather than 64-bit. So you get a factor of 2 for that. If you can tolerate that less precision, you might be in a better position to extract some performance. And as I mentioned, floating point operations really are not the things that cost on these machines. It's data movement. So this conventional wisdom of looking at the operation count for an algorithm when you compare one algorithm to another really doesn't hold up today. You have to look at the communication associated with it, not the number of floating point operations, because that's not going to be a good indicator of the time it takes to solve your problem. So things that have more operations may cost less in terms of the time to solution and breaking that traditional wisdom. And we should be thinking about using mixed precision if we can. So 64-bit is the standard way we think about doing scientific computations. We have the ability to do 32-bit arithmetic that usually runs twice as fast. Some processors allow for 16-bit floating point arithmetic. And on most processors, that's 4 times speed up over the 64-bit. On GPUs, you may even get more additional bonus in terms of that. And today, we're even seeing architectures that have 8-bit floating point arithmetic. So the new NVIDIA processors, the new GPUs that NVIDIA has called Hopper, are capable of doing 8-bit floating point operations. Just a couple of bits, 2 or 3 bits, have been assigned to the mantissa. So if you could tolerate that level of performance, you get incredibly high performance out of it. And those instructions, or that arithmetic, is put in particular for machine learning applications, which can tolerate that kind of thing. Okay, we're on the verge of Exascale. Exascale is being constructed at Oak Ridge National Lab. I'll mention a couple of examples. So 10 to the 18 floating point operations per second. That's a billion operations per second. You know, I have a hard time with that number. I have a hard time conceptualizing that number, a billion per second. Now, I'm talking about 64-bit floating point operations in this context. So that's an incredible amount of computing power. So think about it like this. There's about 7.9 billion people on the planet. And there's about 31 million seconds in a year. So if we think about each person doing 1 computation per second, okay, if you did that for a year, you would end up, they would be, let's see, so what does it say here? So it says a person doing 1 computation per second for a year. If you get everybody together doing it, you'd have 249 times 10 to the 15 computations completed in 1 year. So that's what the planet would do if they were doing 1 operation per second. So it would take the whole planet about 4 years of computing to do what that exascale computer can do in 1 second. Okay, that's the amount of computing power that we have within that device. So it's an incredible amount of computing. There's a machine at Oak Ridge National Lab in Tennessee, very close to my university, which is being put in place as we speak today. That's a machine that's being put in place at a Department of Energy laboratory designed to help with something called the Exascale Computing Project. And it's reported that in China, there are 2 of these exascale machines that are in place already. So 2 exascale machines in China. They have not run the official benchmark that we think about for measuring the performance of a new machine. That's called the Top 500 benchmark. It also goes by the name of the LPack benchmark. And the LPack benchmark says we're going to solve a large, dense matrix problem. We're going to measure the rate at which you can solve that problem on your parallel machine. You have to use LU decomposition with partial pivoting. That's the algorithm that must be used. But you can make your matrix as large as possible, and we're going to measure the rate of execution. And there's some measurements inside to calculate, to ensure that you've gotten the correct answer to 64-bit precision. So that's the benchmark that we usually use to do our measurements and our rating, our ranking of high-performance machines. The Chinese have decided not to run the benchmark, not to report their exascale machines. And we could ask, why would they do that? Why would they decide not to? And I think it's tied up with political decisions. In the past, the US government has informed Intel not to sell components to China. So Intel has basically been embargoed for selling high-tech to the Chinese government, to Chinese installations that are probably used for military purposes. That's the US government saying that. The reaction in China was to say we're going to design our own machines. Those machines are going to use Chinese architectures that's designed in China and that's implemented outside of Intel, outside of the US framework. And those machines are the machines that we know about at these 2 centers here that we believe are exascale in nature. In the US, we have a project called the Exascale Computing Project. It's a project that's 7 years in length, in duration. We're in year 5, so there's 2 more years to go of this project. It's a project that is going to generate 3 exascale computers. 1 is going in place at Oak Ridge today. 2 more are under development. The project overall costs $3.6 billion US. So that's the amount of funding that's going to be necessary to have that project go for the 7-year period. And there are a number of laboratories involved in the project. There's a large group of people developing algorithms, software, and applications for the Exascale computing program. So $3.6 billion over seven years, and what you get for that are 3 Exascale machines. So about half of the money is going into those Exascale machines. So $1.8 billion, $600 million each for the hardware for those machines. And the additional funding is going into the applications that have been identified as important applications for the Exascale computing program, and they're listed there. And you also get a software stack. So there's a large amount of software that's being developed specifically for those Exascale machines, 84 projects, and my group in Tennessee is involved in a number of those projects. If we take a look at the 10 fastest computers today, this is what it looks like. This is a list from November. That's when we last put out the list of the top 500 computers. This is the 10 fastest machines on the top 500. The new list comes out on Monday. So Monday there'll be a new list. It'll probably change this in some way. I know that the number 1 machine will be new from the list. I mentioned the machine at Oak Ridge National Laboratory is an Exascale machine that's just coming up. It probably will be the number 1 machine. But the list today has this computer in Japan. It's at the Riken Computational Center for Computational Science. It's in Kobe. It's a machine called Fugaku. It's based on an ARM processor. So it's based on the processor that you find in your phone, your cell phone. It has vector instructions added to it. So they've enhanced the architecture to carry out vector instructions to allow the processing for the scientific computations to go much, much faster. It has 7 million cores in it, 7 million processors in it, each of those, of course, having vector instructions. It was able to execute the benchmark at a performance rate of 442 petaflops. That's the rate for solving that system of linear equations, and that's 82% of the theoretical peak performance for that machine. So it doesn't run at the peak performance, there's overheads associated with it. 82% is a pretty good number to have in terms of the return or the rate of peak performance or the effectiveness of the peak performance. And this machine is about 30 megawatts in terms of the power consumed. So 30 megawatts under load, as I mentioned, about $30 million to turn it on if it was in the US. In Japan, it's probably a little bit more. And there's something about the efficiency, and that's measured in flops per watt. So it has a pretty good efficiency. It's about 14.8 gigaflops per watt. And then you can look down the list and see the other machines on the list. There's 5 of them in the US, a couple in China. There's 1 in Germany, over in Jülich. That's in operation, a machine in Italy that's there. The number 10 machine is interesting. That's in the US. That's a cloud-based machine. So the other machines are physically on the floor, there for a long period of time, and this is a machine that's run by Microsoft that was assembled specifically to run the benchmark, and they ran it using AMD processors and NVIDIA GPUs in the mix. If you scan down the list, of the 10 machines, 9 of them are using accelerators, GPUs. The first machine uses vector instructions. So that's sort of the mixture of high-performance computing today. We see accelerators being used. We also, if you scan down the list, you'll also notice that Intel and AMD are used in many of the machines. And that's sort of a striking thing as well. This is a snapshot, if you will, of supercomputing going back to 1993. So we started the top 500 list in 1993, and up here is the fastest computer. That's the Japanese Fugaku system at 442 petaflops, number 1. This is the machine at the bottom of the list, 1.5 petaflops is the entry point for the top 500. So that's bracketing the 500 machines, if you will. The blue dots here represent an Excel sheet summation of the 500 computers. So if you were to sum up the 500 computers today, you get 2.8 exaflops in computing power, and you could see where things have been over time. You could see the changes that have occurred, major changes occurring. One computer jumps up in performance, is there at number one for a long time before another machine takes over. The same thing has been true with the Japanese machine. It's been there for 4 times or about 2 years, and it's about to be replaced with the US machine as being number one. We see an inflection point that occurs around here, and the question is why did that happen? What's causing these points where the curves are changing dramatically? Maybe it's Moore's law, Dennard scaling ended. Maybe it's a financial crisis that occurred in 2007. All of those things probably contributed to that change that occurred. It's stunning. My laptop, this device I'm using here to run the slides off of, I can run the benchmark on it. And when I run the benchmark, I get 166 gigaflops. That's a stunning achievement, 160 gigaflops. Out of a machine I use really to read email. That's incredible, right? That's an incredible story in some sense of processing and how things have changed according to Moore's law. And when you take a look at that, my laptop would have been on the top 500 list back here in 1995. It's actually faster than the machine at Los Alamos National Laboratory that was used for nuclear weapons simulation back in 1993, with 1,000 processors in it. Again, just stunning changes over a very small time period. If you take a look at the top 500 list and look at the processors that are being used and the architecture that they have, the instruction set that is, what we see is that the instruction set of most of the machines, in this case here, it's 96% of the machines on the top 500 today are using x86 instruction set, right? Intel and AMD instruction set. I think that's stunning. I'm surprised that it's so large that it captures such a large share of the market. And if you take a look at the GPU side, the accelerators, what we observe is that about a third of the machines on the top 500 use some accelerator, some form of accelerator, some GPU, to offload the computation to get much greater performance than they could without that. And NVIDIA has the largest share of that. So NVIDIA and x86 architecture are the two things. So the big thing today, of course, is machine learning. That's a big topic. It's going to be a terrific tool for scientific computing. I see that really as helping computational scientists get an edge on doing their computation. It's probably not the thing that's going to solve the problem that they're working on, but it's something that's going to help towards solving the problem. Get an approximation, help in getting go in the right direction, and then maybe using standard techniques to refine the solution to that problem. And matrix multiply, small matrix multiply are used in the convolution step. And we have a number of companies, just as we did before, startups, beginning to emerge, providing hardware to help with machine learning problems. There's a market for that, and they think perhaps they can be successful in that market. I would project, based on history, that most of them will fail. But I wish them well in terms of their operations. I mentioned mixed precision, so this is what we have to do our arithmetic today. It's the IEEE standard. We have a standard which talks about quad precision, 128-bit computations, 64-bit computations, 32-bit computations, and 16-bit. If you take a look at 16-bit, half precision, we take a look at the largest number that we're able to represent. It's a number that's on the order of 65,000. So what that means is if your dynamic range of numbers gets above 65,000, you overflow. So it's a very tight range, and if you're going to use the IEEE 16-bit format, you better really think about scaling your problem to fit within the context of those large numbers. Google said that's too small. We need bigger numbers. We need to be able to represent bigger numbers in 16-bit arithmetic. So they said, forget about the IEEE arithmetic. We're going to have our own arithmetic. So Google's big enough, they can do that. And their TPUs and their other processing capabilities, they define bfloat16. bfloat16 has 8 bits assigned for the exponent and 7 bits assigned for the fraction. If you compare that to what IEEE says, you only have 5 bits for the exponent. The 8 bits for the exponent gives them the same exponent range as single precision. Of course, they have to reduce the mantissa or the accuracy that's achieved, but for many machine learning problems, that's not an issue. NVIDIA also is in the game of machine learning, and they say, well, we're gonna give you hardware which can do another format. They call it TF32 format, and that runs very fast. It's a hardware format. It's not a data storage format. So when the data gets to the processor, it uses this format to carry out its computations, and then things happen, the truncation happens perhaps on the way back out to storage. And with that, they basically allow for 8 bits of exponent and 10 bits of fraction, sort of a compromise between these two formats to give you a better way of doing business. And we're starting to see the big vendors. We got Google, we have Amazon, we have Apple. They're saying, forget about traditional processors. We're going to design our own processor and use our own processors in our computing center. So that's what they have at Google with their TPUs, at Amazon with their Gravitons, and Apple, of course, has their M1 processors, which they're deploying on all of the equipment that they have. So they're not going to commodity processors. They're developing their own processors. These companies have a tremendous amount of resources available. They have a tremendous amount of money available. And they can afford to go off and design their own processors that'll best suit their applications. Where most of us in the scientific area, we really can't go off and design our own processors. I mentioned the format for 8-bit floating point that NVIDIA has. So this is the 8-bit floating point formats that they actually have 2 of them. One gives you 2 bits of precision, and the other one gives you 3 bits in terms of their 8-bit floating point 8 representation, and the floating point 8 screams on the hardware that just came out from NVIDIA. Let's see, I want to turn to that story of data movement and floating point operations. If we take a look at data movement and floating point operations over time, so I've plotted here processors over time, and what I'm plotting against is the number of floating point operations that can be performed over the amount of words from memory that can be transferred. So think of it as the rate at which you can do the operation and the rate at which you can deliver the information to the part of the machine where you're going to do the operation. So we want that to be in balance. So I want that to be a ratio of 1 to 1. So in the early days, we had processors that had a good balance between data movement and the floating point computation, and they were able to keep up. Floating point in those days we would consider to be expensive compared to data movement. But as time went on, the floating point operations became more and more inexpensive, and the data movement became greater. This is the memory wall we talk about. So we have the processors being able to do operations at a certain rate, and the rate at which they can do them changes at a greater rate than the data rate that we can move the information in over time. So the memory technology hasn't kept up with that rate, and the result has been we have processors today which are in basically you can do order 100 operations in the time it takes to move that one piece of data. So data movement is very expensive in terms of that. If I take a look at my laptop and think about doing some numerical computations on its simple memory hierarchy, my laptop has some memory, 16 gigabytes of memory. It has a cache, 6 megabytes. It has a CPU. And the rate at which it can do operations, the cycle time, says that this processor can run at 56 gigaflops. That's the single core of this processor. That's what it's capable of running. The data rate that I can move data from memory up is at 25.6 gigabytes per second. So that's a data movement rate. And now the question is, when I run problems on my laptop, how much performance can I see? Do I get anywhere near this 56 gigaflops on my laptop? or is it hampered because of the data movement? So that's the question I'm trying to answer. If I take a look at the balance on this machine, I have 31 floating point operations for every word that I can move. So that's the imbalance. 31 floating point operations for every piece of data or word of data I move from memory into the cache of that system. And that puts my laptop in this component of that graph that I was showing. So what happens when I do an operation? So let's take a very simple operation like a vector operation. In this case, I'm doing a DAXP. This is taking a scalar multiple of one vector, adding it to another. The data's in memory. I stream those two vectors into the cache, into the part of the machine that does the operation, and then I stream that one vector back out into memory. And when I do that operation for large vectors, even small vectors, I end up with a graph that shows performance that looks like this. So the peak performance I can get out of this operation is at 1.6 gigaflops. That's the theoretical peak. That's the achieved peak that I can get out of this machine. So I had 56 gigaflops was the theoretical peak, and I'm achieving 1.6 gigaflops for a vector operation. If I raise the level of granularity, going to a matrix times vector operation, I end up with a graph that looks like this when I actually measure it on my laptop. So I get about twice as much performance. 3.6 gigaflops per second is the performance I get out of this matrix times vector operation. So it's a bit better, but I have a lot of data to move. I've got n squared pieces of data, and I'm doing order n squared operations, and that's the rub. That's the problem with doing that. But if I do a matrix multiply, where I have n squared pieces of data and n cubed operations, I'm capable of using that cache and getting reuse of the data that's in the cache and effectively driving the processor at 54 gigaflops, very close to the theoretical peak of the machine. So that's really what I strive to do in my computations. So again, this classical analysis of looking at the processors and looking at how many operations you can do per cycle, you may be misleaded if you take a look at your algorithm and just look at the operation count of the algorithms compared to another algorithm. I mentioned this LPack benchmark. It was done a long time ago. It was started back in 1997. It does a dense matrix calculation. Back in 1997, that dense matrix calculation may have been a good reflection of what applications were capable of doing on the machines. Floating point operations were very expensive then. Data movement was not as expensive. And this benchmark is highly intensive in terms of floating point. In fact, it's matrix multiply at its core. So if you do good at matrix multiply, you'll do good at this benchmark. However, the architectures have changed. Arithmetic is now inexpensive. It's over-provisioned in our hardwares, and as a result, this benchmark may not be a good reflection of what happens in real applications. So using this benchmark, I think, needs to be thought of as an old benchmark, and maybe we should be thinking about new benchmarks that really stress the appropriate things in the machine. So you really don't want to design a system based on this benchmark is the bottom line. You want to design systems based on other benchmarks if we have a common mix of problems. So we have a new benchmark, of course, and this benchmark is going to look at problems that we think about solving on our large-scale machines. So if we take a look at those machines that are in use today, we think about solving three-dimensional partial differential equations. That's what they're used for. And that three-dimensional partial differential equation gets discretized. That discretization leads to, again, a system of equations, but the system is quite different. It's not dense, it's a sparse matrix, and we're going to use a sparse matrix technique on it to solve that problem. The sparse matrix technique usually has a preconditioner. It's an iterative method. We have to move the matrix, which is a sparse data representation. It's a representation where we have a lot of zeros in it, and we ignore the zeros, and we just move the active part of the matrix together with the preconditioner to do the problem. And when we do run that benchmark on our machines, we end up with another chart. This is the top 10 for this benchmark. And the top 10 for this benchmark has the Recon computer, again, number 1. So it's a very powerful system. It has good bandwidth, so it could sustain the computation. The benchmark, the LPack benchmark, got 442 petaflops. This benchmark gets 16, but that's the fastest one. So you see the difference between a matrix multiply and a sparse matrix kind of operation that gives you back roughly 3% of the theoretical peak performance for the machine. And if you scan down the list, most of the machines are getting around 2-3% of the theoretical peak, which is really, some people are embarrassed by that. Some people say, you can't tell the people who give us funding that I'm only getting 2 or 3% of the theoretical peak on these machines. You're really wasting the resource in some sense, but this is the reality of it. And most machines are in that category. We have a machine down here at the bottom that gets about 5.6% of the theoretical peak, and that's a machine that comes from Japan. It's a machine from NEC. It's a machine that has vector instructions. Again, they've designed the machine to have very good balance between data movement and floating point operations, and that shows up. So this chart here is looking at different machines. The x-axis is the rank of the machine, and the y-axis here represents the execution rate. So what I'm plotting here are the theoretical peak numbers, the black dots. The green dots are the LPack benchmark numbers, the numbers that are in the top 500 list, and those are the dots that come from the HPCG benchmark, much lower, sort of bracketing what we would think of as numerical computations. So let me just conclude and say the software design that's taken place over the last 40, 50 years really follows the hardware. So the software has evolved as the hardware changes. And the way I think of this is every decade or so, the hardware guys develop a new piece of hardware and they throw it over the fence. And the software applications people have to scramble to try to make use of that hardware, design applications, design software that can effectively use the components in that machine. It takes us about 10 years to do that, and then a new architecture gets thrown over the fence, and we have to go through that process again. So we should be thinking about experimenting with mixed precision. Because of machine learning, mixed precision is going to be here for a long time, and as computational scientists, we should look at trying to exploit that architectural feature in our scientific computing and perhaps doing a better job with that. We should also remember that counting floating point operations is perhaps not the best way to measure an algorithm. We should also be thinking about looking at the amount of data that's moved within that algorithm and trying to minimize the amount of data because of the importance of that. I like this idea of responsibly reckless algorithms. So a responsibly reckless algorithm is an algorithm that runs a problem, and it may use an algorithm which is unstable. It may use an algorithm which may get the wrong result, but it has a way of checking to see if it's gotten the wrong result. And the assumption is if you run this algorithm, it'll run much faster than the conventional algorithm. And if it gets the wrong results, you can abandon that computation and go back to the classic algorithm and take a performance hit in that context. But most of the time, you'll be able to run in this responsible way of checking to see that your algorithm, in fact, has done the right thing and maybe take a shortcut. So software is really not about just hacking out a piece of code. It's not a sprint. I think of it as a marathon, designing something that will be used by community in the long term, trying to build into that software a number of features, attributes, accuracy that we can, the best accuracy we can give it, get the community involved in the development and also the maintenance of the software, look at state-of-the-art ideas, look at performance, portability, productivity, readability, and also reliability in our algorithms. So with that, I'll end, and I'd be happy to answer any questions you might have.
Okay, let's thank the speaker. All right, thank you, Jack, for the very nice presentation. So just as a disclaimer, we are still being recorded and streamed, but I hope that doesn't discourage you from asking questions. We have microphones that we can pass on to you. And now I would like to open the floor for questions. Okay. Well, there's one, and there's one.
Throw it. You can throw
Chris,
the box.
you first.
Yeah, I'll throw that. Thank you. Jack, thank you much for that very interesting talk and the path through history. When you were talking about the LPack benchmark, dense linear systems, which profit from the fact that there's many more operations to do than there is data to do them with, and then you contrasted it with the sort of green LPack benchmark, which is in some sense the more sophisticated algorithm that underpins the whole thing. That we use structure, we get sparse systems, and we basically only have as much data as we do operations, more or less. Okay. Now with machine learning, we have the luck that it's again matrix-matrix multiplication, so our preferred operation at the core, so that saves us a bit more operations than data. But how do you view that in the future outside of the AI world? Isn't it such that when the problems get big, they have structure, and you not always have this comfortable blanket of having more operations than data?
Right, so you're pointing to a fact that we have different applications, many of them important applications, and we have to understand and design hardware which can effectively run across a wide set of applications and design points. So it brings up how our machines are built today. Our machines are built using processors, which are conventional processors, tied together with an accelerator where we can do those matrix operations very effectively. And in the future, I would project or forecast that architectures would evolve, and they would evolve to have more things added to that set of components. So not only do you have processors and GPUs, you have a machine learning component. So you have another piece of hardware which can be attached to that collection of things to do that specialized thing. And if you have problems that can benefit from neuromorphic computing, we have another device added to the ensemble of things that can effectively do the neuromorphic computation. Or if we think about optical computing, we have a device which takes optics into account, and the interference of these two optical patterns gives us a multiply out or something like that. We might add to that collection optical computing. And of course, there's always the future could hold for us quantum computing. And then we have a quantum device. I don't see quantum as replacing all the other stuff there. I see it as another component that we would have at the disposal of the computational scientists to help them specify part of the problem, perhaps, that could be effectively solved or approximated using that device. So again, it's a tool that'll be added to the chain where appropriate, and a user would maybe be able to dial up which of those components they purchase from some vendor of the future or build.
That basically means you'll have more heterogeneity.
More heterogeneity, yes.
More different stuff in the system with different capabilities, and we have to learn how to play on that larger set of capabilities. Like right now, you suggest at the end, use mixed precision because we're going to have it.
Exactly.
Okay.
So as computational scientists, we have to, we're in an unfortunate situation, right? We don't get to design the hardware. Somebody designs the hardware and throws it over the fence. And now we're stuck scrambling to try to use it. And they may be in a position to dial up some components that we use, just like we can dial up how many GPUs we add on to the ensemble of processors that we have. But we're not in a situation, we don't have the resources that Google or Amazon or Facebook or Microsoft have to build their own hardware, or Apple, to build their own hardware to solve their problem very specifically. You take a look at Apple, and they're designing chips to take a lot of the software components and replace them by chips in the processor. So our phones have many CPUs in them doing specialized things. And maybe that's a way in the future where some of us can get that benefit. They have chiplets now, which are a design of a chip where we add on to that chip components that may come from different manufacturers that are specialized to do certain parts of the computation. So I could see an FFT chiplet being added onto a chip that would help with that part of the component, that part of the computation.
Thank you. Okay. You have shown that x86 instruction set is the most important instruction set on the HPC machines. Do you think ARM becomes more important in the next years?
Yeah, that's interesting. I would have thought so. I would have thought there'd be many more ARM processors on the top 500 list as an example. I think there are three machines. Maybe that'll grow. But I was struck by the fact that we don't have more. Just because of the common use of it for other things and people's awareness of it, I think there's hope that it will grow in the future. But again, it seems retarded. It seems like it's taking a long time for ARM to break into what I'll call high-performance computing. Although the Fugaku system is using an ARM architecture, so that's one of the biggest machines I know about that is using that.
Okay, and do you see a chance or risk in diverging or in a heterogeneous world? So we have Apple and Google developing their own architecture. So do you see a chance or risk?
I'm sorry, I missed the first part. So
is there a chance or risk if there's a heterogeneous world of architectures?
So I would say there's no risk for Apple or them. I think they're going to design their products to suit their needs quite well. From our standpoint, when I look at the machine that's being put in place, the new Exascale machine at Oak Ridge, 98% of the performance comes from the GPU. And how many applications really can use the GPU today? So if your application is not built for GPUs, that you're wasting that resource. So that machine is not for you. So we have to realign, and again, it goes every 10 years. We have to redesign things. So yes, we have to redesign things for this architecture. Again, it's not a new story. I remember people originally complained about vectors, and then when parallel computing came, people complained about rewriting their application for parallel computing. We got over all that. People now understand how to write parallel programs for major scientific applications, and now they're complaining about GPUs. So it's a process. We go through it, we understand it. Again, we get thrown a piece of hardware over the fence, and we scramble for the next 10 years trying to figure it out. It's not a very good use of time, I would say. Yes.
Okay. Yes, I really appreciate your talk. It was very interesting. So in your talk, you mentioned that previously there were many problems with the communication, for example, and then people came up with the standards. And nowadays we are seeing kind of the same problem in the architecture. So we have many CPUs, GPUs, and also we have this new architecture for the CPU for the ARM, as also been mentioned. Do we have any standard nowadays, or will we have any standard in the future which can potentially solve these difficulties for having performance portability on each device? So can we have, for example, the same efficiency level on different architectures in the future, or there will be the same situation as we have right now in the future as well?
Yeah. So can we get better efficiency in our applications? So if they put a group of application people in a room and had them design a computer, we would probably get a computer which would be more balanced for the applications. It might be very expensive though. So there's always a trade-off here about what you're willing to pay for that ease of use or ease of extraction of performance. What I've shown is that people would rather use commodity processors from Intel, from AMD, use commodity GPUs from NVIDIA or AMD, use commodity interconnects. I didn't really talk about it very strongly, from InfiniBand interconnects, and put them together to build a high-performance computing system because the cost is low. They can have on paper high performance but low cost. So that's the wrong measurement in my mind. It's about productivity. What's your productivity is more expensive. Your time is more expensive than the computer. That's going to be the bottom line. So I want to make productivity be a major thing. So I'd rather change that and not use those commodity processors, do something that lets us express the algorithms in a way that can better take advantage of our time and be more efficient in terms of the time to solution for our problems. So it really should be about us sort of optimizing our time in terms of the development and analysis of the problems, rather than to come up with a cost-effective piece of hardware which may be hard to use and take us much longer to implement in order to effectively do it. So I think that's imbalanced right now. And one way to rebalance it might be to have the architects listen to the application people closer. That's a hard thing. We call that co-design. A lot of people talk about co-design, but really having a co-design machine is something that really doesn't happen today.
But maybe as a second question, do you think, or what do you think was the main reason for those startups that you mentioned in your talk to fail? And why do you think that the new generation of startups that you just showed will fail in the future?
Right. So we have a lot of examples of failures in using different computer architectures. So why did they fail? The bottom line is they don't have enough customers. Okay, so they failed. They didn't have enough people buying into their hardware. There was maybe too much diversity. The expectation wasn't met with performance. The hardware didn't work. It failed. It broke. It didn't really work. There wasn't software for it. There's many reasons for the failure. In the end, supercomputing, scientific computing, is not what's driving the industry. It's the guys at Amazon, Facebook, Microsoft, Apple. Those are the guys driving the industry. Those guys have a tremendous amount of resources at their disposal. They can build their own hardware. That's an incredible situation to be in. And the rest of us have to use commodity off-the-shelf parts to build our stuff, and that's going to be inferior compared to something you could design specifically to solve your problem. And it's just too costly to do. And companies that try to do it are failing. We will fail. So will the machine learning companies fail? I would guess most of them will. But they're going to generate ideas. So those failures that occurred with the other systems, the ones that built these parallel machines, hey, that generated many students who got interested in parallel computing, and led to educating a whole group of people in terms of parallel computations. It led to new ideas being exposed, led to new algorithms being created. So I would say there's advances that occurred as a result of that, so it wasn't wasted, but it couldn't sustain itself in terms of an industry.
Mm-hmm. Yeah. Thank you.
This one way in the back.
Thank you. Do you think that if we change our hardware every 10 years and application designers would also want to change stuff in there, that this is a big chance for more open and more accessible or better extensible instruction sets like RISC-V, for example?
So it should be. It should be a great thing. So we should have a gradual change that takes place. We shouldn't have to wait that 10-year decade for new hardware to be thrown over at us, that we react in a way. We should, again, it comes down to this idea of co-design. We should be in the same room with the architecture people, with the software people, with the application people, to design something that makes sense. It's going to be more costly. We should go in with that assumption. It will cost more to do it, and things may fail. So this is the other thing that we almost don't tolerate. People don't tolerate failure, but we're in research. I fail all the time. I have new ideas and it doesn't work, and that's a good thing. That's I learn from my mistakes and I do better the next time. So we should be prepared to fail, and failure should be an option, and it's okay when it happens. I tell my student, we have students come in, and new students always want a problem to work on. So I give them a problem to work on. I say, here, go off and think about this problem. And they go off and think about it. They come back in 2 weeks and say, I can't figure out how to do this. I have no idea. And I said, perfect. It's a research problem. You shouldn't know how to do it. You should go off and think about it and come back and have some ideas about how you might tackle it. So go off and think about it a little bit harder. So, having a failure like that is okay. That's an option. And, being able to structure things and being able to learn in some way from that is okay. So we should be in a position not always to have a success, we should be prepared to fail occasionally and redesign things better based on that failure.
Thank you. Also for the motivational words.
One last question, and then we have to close the session.
Way in the back of the room there, the guy's, I can almost see his hand.
Okay, my question refers to the algorithms used in supercomputing. You mentioned that we use algorithms that avoid making a lot of use of data movement. And my question is, why do we limit ourselves to such algorithm instead of focusing our...
Takes to move the data. And I think that would be a good project. We should invest more in terms of hardware which would minimize the time it takes to move data. And people have thought about this. People have architectures which try to do this. And the simplest architecture that we have that tries to minimize the data movement is something called processor in memory. So the processor is not over here and the data over here. The processor is literally stuck in the middle of memory. So we have lots of processors scattered across the memory so that the processors are very close to where the memory is located, and the data comes to the processor, if it's in the locale, comes to it very quickly. So that's certainly one way. The hardware guys are trying to help us. I shouldn't say that they're working against us. I think about stacked memory as an example where we get some benefit from three-dimensional stacking. So memory is not two-dimensional anymore. There's a three-dimensional effect to memory, and data comes much quicker as a result of that. So the data is getting to us a little bit faster, but the problem is that the processors are getting much faster at a higher rate than the memory is coming to us. So Moore's law, Moore's law is not dead. It's not dead. It's still here. Dennard scaling is over, but Moore's law is still with us. So we're getting maybe not exactly at that same rate of doubling every 18 months the number of gates that go on to new devices, but it still is increasing, and that's going to be with us for a while. So we will have that increase in terms of the number of processors on a device. That's going to continue, and we should continue to work on coming up with strategies and ideas that help mitigate the problems with memory, the speeds of memory.
All right, then let's thank the speaker again. So, Jack, thank you again for this very inspiring talk. So I brought a little gift for you.
Aha.
And so this is a bottle of gin from the Black Forest. So we're not exactly here in the Black Forest. It's we're close, but not exactly here. It's a Darmstadt, and the Black Forest is a little bit like Knoxville and Kentucky.
I see.
And so, like you, this gin has a long list of awards, and the distillery claims that it's even the most awarded gin product in the world.
Excellent.
And so I thought a distinguished spirit for a distinguished speaker, distinguished mind, is the right gift for you. And well, it has been an honor to have you here. Thank you again.
Well, thank you so much for this very distinguished bottle, and I'll enjoy it. Thank you, Felix, and thank you for your attention.
Okay, yeah, thanks everyone. This closes the session, and I thank you very much for your attention. I wish everyone a great weekend.
Oh yeah.